The next presentation is by Dr. Izzy Inerhunwa from OFR Consultants in the UK. The presentation is on modeling of load-bearing light gauge steel frame walls exposed to fire on both sides.
So LSF system, light gauge steel frame walls typically have cold form steel studs, which form the studs, and then you have the cold form steel also forming the top track and the bottom track. You may or may not have insulation between the walls, and you then have that all those sandwich with sheeting board, which is typically gypsum plasterboard. The gypsum plasterboard is fixed to the studs and the track with screws, which are spaced at certain intervals. Um, there are different configurations of this type of wall systems, depending on whether you have the cavity of the wall completely filled with insulation, or the insulation could be, you could have it halfway, like in this case, or you could have the insulation in between two layers of plasterboard. And there are different stud sections that are typically used, but the common one is the C profile here, which is what this study is based on. If you look through literature, terminologies used to describe this type of wall system vary. Typically, you see light gauge steel frame walls, or lightweight steel frame or steel framing, cold form steel walls, thin wall steel element. They generally refer to the same class of wall systems. They're typically applied in residential buildings and industrial buildings, and the walls could be used as fire separating or non-fire separating. Non-fire separating means it's expected that the wall will keep out fire from progressing from one room to the other, and non-fire separating, they're just as a fire, as a partition, not serving any fire purpose. They could also be load bearing, where they are required to carry some load and transfer them down to the foundation, or non-load bearing elements. And they are seeing increasing usage within the industry because they are lightweight and they are very quick to and fast to construct and erect. So what were the industry concerns related to this was, many of us will be familiar with CROSS. CROSS is is an acronym for Collaborative Reporting for Safer Structures. So it's like the voluntary reporting systems where you can go in, and if you've noticed any design failure or design flaw, either while reviewing a work or seeing something on site or anywhere, you can report that voluntarily, and the CROSS will look at your review and then see if that is worth putting that across to the industry for the industry to be aware of. So there are several CROSS reports that have been released relating to this light gauge steel frame walls, where the reporter was concerned that the walls are typically tested by the manufacturer to be exposed to fire on one side only. But typically, what they found is that there are some cases where the walls could be exposed to fire on two sides. And what the reporter was concerned about is that once you have the fire exposure on both sides, that could change the rate at which heat transfer within the steel studs, which if it is load bearing, can then impact on the time it would take to fail and its load bearing fire resistance. So they were then saying that these are wherever you have a wall that has been tested on one side, they think that it's a concern if the wall is going to be exposed on two sides and the wall has not been tested on that. So like the case I just described now, it's actually very possible that the walls will be exposed on both sides, because you could have like the picture on the right, where you could have a flat, and you then have your light gauge steel frame wall in the middle, which is also acting as load bearing, and then you could then have the fire start here and then travel to the other side, such that at a point in time during the fire, both sides of the wall are then exposed, whereas the wall was only tested for one-sided exposure. Or you could have a case where you have a fire starting from the inside and then breaking out from the window, and then you then have simultaneous exposure from the external exposure and then the internal exposure. So such cases are possible, and in those cases, that's what the concern that was raised in those CROSS reports. So before we began the study, we looked at what the current guidance in the UK says about this in terms of exposure conditions for different structural load-bearing elements. So for generally, there are three categories of exposure conditions that are defined within the guidance. So it's either condition A, where you have exposed faces. This is typically for structural frames like beams or columns. So you test the element for where the number of exposed faces that are exposed to fire. Like, for example, if a column is designed, it is going to be exposed to fire on all four sides. It's expected that the column is tested as such. So for load-bearing wall, it is typically on each side separately. So you're not expected to design it to be able to um, um, resist fire on both sides simultaneously. You only look at one side at a time, which is what a lot of the manufacturers were basing their testing on. Or in some cases, you could have it on just for external walls from inside the building only. You don't even need to consider from the other side. As a result of this, there were several what is known as FAQs and frequently asked questions that were raised, and then the government then provided a bit of guidance. That one of those was people wanted to know if the exposure conditions recommended in the table I just showed, if it's applicable to all situations. And if the answer is no, the other question was then if we said no and the building elements can be, it's not described by all the cases in that within the table, is it possible to look as well? What can they do in that instance? So as a result of this, the question that was asked was that, is this an issue? Does the number of faces that a wall, especially light gauge frame wall, the number of faces of this type of wall exposed to fire, does it affect the load-bearing fire resistance? And is there a way we can then develop design approaches to be able to consider this exposure condition from both sides? And are there any practical implications? Because manufacturers currently have series of tests which are only based on one-sided. Does that mean for all the wall systems they've designed and they've manufactured today, do they have to go back and then retest those for two-sided? Or is there a way they can look at a wall that is tested on one side and what the equivalent fire resistance would be when it's then exposed on two sides? So to do this, we looked at literature. We couldn't see any testing that was done for walls exposed on two sides. There were lots of testing that be done on walls exposed on one side. So we thought that the first thing we needed to do was to do an experimental study. In that experimental study, we looked at two cases, one where you have no insulation and the one where you have full cavity insulation. And the wall was 3 meter wide and 3 meter in height. So we looked at first case where the wall is subjected to fire only on one side, and then we looked at another case where the wall is subjected to fire on both sides. So in all, we had 4 cases that were tested. This was large scale fire testing in the furnace. So these are pictures from the test. This is the two-sided exposure with some thermometers and thermocouples placed at specific locations on the outside of the wall, on the board, and within the steel studs inside. This is for the two-sided, and this is for the one-sided case. So just a short video to show you one of the results for one of the tests for the one-sided case. You could see the runaway deflection that occurred during the test, and that was around 156 minutes. Something to mention here, we couldn't record the two-sided because we would have to have placed cameras inside the furnace, and that wasn't possible at the time. Maybe as time goes on, we'll be able to have a way to overcome that. So these are the results from the test. It showed that where you have two-sided versus one-sided heating, two-sided generally gives you uniform temperature distribution which makes sense. And then because you're having temperature from both sides, heating from both sides, and that means the stored temp would likely be uniform. But where it is one-sided, you have no uniform temperature distribution. And this was crucial because when it's uniform, the way the stored behaves is different from when it's not uniform, because additional bending can be introduced under non-uniform heating. And the rate at which that temperature increases also differs for two-sided and one-sided. And this is for the lateral deflection, where we observe runaway deflection for both cases. We've published the results of the testing in the paper. So if you want more information about that, you can get that, but the focus of this will be on the SAFIR modeling. So summary of findings from the experiment is that one, we observed that the load-bearing fire resistance reduced significantly down to 44% when the wall is not insulated, that is with no cavity insulation, and down to 62% when the wall is insulated, which was significant. So that means if a wall has a fire resistance of 60 minutes on that one-sided, you should not be using that for two-sided, because if the load-bearing capacity of the wall would have reduced significantly when it's now exposed to fire on two sides. We also observed that for two-sided exposure, the temperature distribution is uniform, whereas for one-sided, it is non-uniform because you have heating only from one side. And the temperature gradient due to cavity insulation in one side plays a role because where you have cavity insulation within the wall, that also slows the heating across the stored section, and then the non-uniformity of the temperature is more pronounced in that instance. And crucially, one of the takeaways was that fire resistance classification for one-sided exposure should not be extrapolated for two-sided, meaning if you have a wall that is tested to one-sided, you should not assume it will achieve the same fire resistance when it's not exposed to fire on two sides. So this generated a lot of conversation in the industry, and we wanted to see how we can help. I haven't done this test. How can we then help to see if we can expand this? Is this prevalent across all cross sections, across different insulation types or insulation configurations, across different fire types, different number of plasterboard layers? So that is where we then say there's need for further study so that we can answer this question. And that's where we said, one, we need to extend the analysis beyond the test condition, the loading. We've only applied a specific load. What if we change the load ratio? Does that affect the fire resistance that is achieved on that two-sided exposure, the insulation type, the number of plasterboard layers, the fire model, and also, because in reality, it takes time for the fire to travel from one side to the other side. So we then use SAFIR to develop a sequential finite element model that was done in two stages, the thermal analysis, and then the result of the thermal analysis were then used to run a mechanical model. For the thermal model, we just as we tested, we looked at case without cavity insulation, like in this case, and then we looked at a case with full cavity insulation. So we did a 2D model first to then compare the temperatures we get with what we got from the test. And these are the temperature dependent thermal properties, the specific heat, thermal conductivity and density of the gypsum board, and thermal conductivity of the mineral wool that was used as the insulation. One thing to note here, what we observe is that because when you are exposed to fire on two sides, because of the moisture within the plasterboard and the way the ablation process works, the thermal conductivity curve that was used for the one-sided could not mirror the test results. So we had to alter that. So it's something when you're modeling walls exposed to fire on two sides, there's because of the heating on both sides, we needed to alter the apparent thermal conductivity that was used to for us to validate the FE model. So in validating the FE model, we use ISO standard, the test in validating the FE model. So in comparison with the experiment, we use ISO fire curve, just like in the test, one side exposed to fire for the one-sided, and for two-sided, both sides exposed to the ISO fire curve. So these are the results from the test. Comparing the result from the experiment with that of the finite element model, we showed good agreement in terms of the thermal model. And also in terms of temperature distribution, you could see when it's two-sided, the temperature of the stored is uniform from 30, 60, 90 up to 120 minutes. But when it's one-sided, you could see there's a temperature gradient created from the exposed side to the unexposed side. This was the case for the with no insulation. Then the case with insulation, something similar was also experienced, where you have for two-sided, you could see uniform temperature distribution, and for one-sided, the non-uniform temperature distribution, you can see the exposed side is way hotter than the unexposed side. So we then use that temperature to then do a mechanical modeling where we use shell elements. We only modeled a single stud because in the test there were 6 studs. And then we divided the total load that was applied during the test by 6 to get the load that will be applied on one of the stud. To simulate the restraint provided by the plasterboard, flange restraints were provided at 300 mm spacing, similar to the spacing of the screws on the plasterboard. The top of the column was loaded and the bottom was boundary conditions were applied as shown. In terms of applying the temperature, what you would see in some studies is that this temperature will be a temperature gradient increasing from the bottom to the top, increasing from the bottom and reducing towards the which higher the bottom and reducing towards the top. But what we did is to take the temperature at the middle of the web and then apply that throughout the web, temperature at the middle of the flange, apply that throughout the flange, and temperature at the middle of the top flange, apply that throughout the top flange for the one-sided. But for the two-sided, because it was uniform, we took the average temperature of the flange, the web, the bottom flange, the web, and the top flange, and then apply that throughout the entire cross-section. Yeah. So these are from the test, pictures from the test, and then picture from the model, which I would say we didn't get like picture from, because of the plasterboard covering the studs, we couldn't get at the time at intermediate time before failure, so we could only get the failure of the stud, picture of the failure of the failed stud after the end of the test. But it looked like the model showed that the stud already failed. You can see several buckling modes already occurred as shown in the test. So we also compared the time to failure for both the test and FE, which was very good accuracy. So we then did parametric study because we wanted to see, now that we validated our model, our SAFIR model, wanted to see different types of fire curve, the ISO fire curve. Where you have parametric fire curve, generally you could have, it's a short hot or long cool curve. So wanted to see how that affects, if that plays any role. And also when your wall is exposed to fire from the outside. We also looked at external fire curve. So these are all the 4 type of fire models that were considered. We looked at the influence of plasterboard layers from 1 to 3 layers, different insulation type from no insulation to cavity insulation and external insulation, different time for the fire to travel from one side of the wall to the other side of 0 up to 20 minutes, and then different load ratios because the test was only done at one particular load ratio. So we wanted to investigate different load ratios as well. Because of the number of cases from the parametric study, so we use Python to then automate some of the process throughout in terms of creating the geometry and the material properties. Many of us are familiar with the SAFIR. You then create a geo file and a G4S file, which contain the geometry and the material properties and the boundary conditions that you've applied. So we're able to automate that process as well. We're able to modify SAFIR input file automatically, where we have the same model and we are just changing maybe the boundary or the fire type that was applied. We could run a Python script to then automatically edit the input file, so we don't have to recreate the model from scratch. When doing your thermal analysis, whether 2D or using the shell, you work with .tem file, the .tsh file, so we're able to have Python script that could read this and modify this for the different cases, which made the process faster. And also to post-process our results, we were able to use Python to read through the XML file that was created, which is one of the advantages of using SAFIR because it gives us the flexibility to be able to run a number of parametric cases and automate some of the processes. So result of the parametric study showed, we looked at the effect of the wall insulation. We also looked at the effect of the number of plasterboard layers. We looked at the effect of fire exposure type and time lag. So for insulation, it was found that if you see the external insulation took the longest before you could see rapid increase in temperature. So that showed that the external insulation case performed better. And also, as you increase the number of plasterboard layers, the fire resistance of the wall increases, which made sense. Also, the fire exposure type, what we find out is that the ISO curve on that two-sided has been shown to be a conservative model to use in most cases, because it gave you the most severe eating rates in many of the cases. And then that means we could use that without having to go under refires and be confident that the result will be on the safe side. We also looked at the effects of time lag up to 20 minutes. It showed that time lag did not really affect it when you looked at only up to 20 minutes, but we think that if you increase the time lag to 30 minutes, that you may begin to see significant differences in the result. But also, we also want to see how realistic is it before we increase that further in our further modeling, what is the time that will typically be expected for the fire to travel from one side before we then increase it further. And so in summary, one of the key summaries from the parametric study is that one-sided exposure gives you non-uniform eating, two-sided is uniform eating, and that in terms of the insulation type, external insulation perform better than no insulation, which also perform better than cavity insulation. In summary, when it's exposed to one side, cavity insulation perform the least and external insulation perform the best. Whereas for two-sided, with no insulation, cavity insulation, there was no significant difference in the result, but external insulation performed better than both the no insulation and the cavity insulation case. So we also looked at the load-bearing fire resistance in terms of critical temperature. So if we have a wall that is exposed to fire on that one side and two-sided, what is the drop-off in the fire resistance that is achieved? We could see when you have one layer of plasterboard based on a critical temperature of 430, the under one-sided was 30 minutes, but for two-sided, it showed that it did not pass at all. So you couldn't use that if the wall was to be exposed to two-sided. Whereas for two layers, it's achieved 90 minutes on that one-sided, but for two-sided, it was 60 minutes based on the critical temperature. So this table is showing cases where the temperature exceeds 430. We'll consider that to be failure, and anything below that to be passed. And where you increase the plasterboard layers to 3 layers, for example, you could see 120. The temperature is below 430, so which means it achieved 120 minutes. And for 3 layers, the temperature that is lower than 430 is 119 minutes. So if you go to 120 minutes, the temperature already exceeds 430, so 120 minutes will not work. So that means when it's 3 board layers, for the fire resistance achieved there is maximum of 90 minutes. So we'll observe that there's a drop-off of approximately 30 minutes as you increase from 1 layer of plasterboard to 3 layers for both from one-sided to two-sided. So we also looked at runaway deflection, where you could see the failure time for different load ratios. So this was case for load ratio 0.2 and load ratio 0.6. So for one-sided, it was 162 minutes for a load ratio of 0.2, but for two-sided, it failed at 57 minutes. Whereas if you increase the load ratio to 0.6, one-sided still failed later, but the difference is not as significant as with a load ratio of 0.2, because the two-sided then has a load failure time of 51 minutes. So in conclusion, what we'll find is that from our study, two-sided fire exposure gives uniform temperature, whereas one-sided is non-uniform. In terms of insulation type, external insulation is the most effective. Also, as you increase the number of plasterboard layers, the fire resistance of the wall would increase and the temperature would reduce rapidly. The fire model ISO fire curve was shown to be conservative compared to all the other cases, and introducing a time lag of 20 minutes reduced the maximum temperature marginally, but not significantly. But we think maybe if we increase that time lag, there may be more benefit, which we'll investigate later on. In terms of load-bearing fire resistance, two-sided fire exposure significantly reduces the load-bearing fire resistance, and the difference in load-bearing fire resistance changes with the load ratio of the studs. And then there's also been policy implication as a result of this study, where we've made a recommendation to the building safety regulator in the UK regarding amending the table B3, which I showed earlier, so that it can cover cases where walls are exposed to two sites, such that designers know that when you have such design cases, you should have walls that are tested specifically for that type of exposure condition. There are ongoing work currently, which we are doing further numerical modeling, which mainly the mechanical, because we've finished all the thermal modeling with SAFIR. We're cracking on with the numerical modeling now, because we want to be able to establish a basis or method for if you have a one-sided fire exposure, how do you then extend that to determine the fire resistance of the wall when it's now under two-sided fire exposure condition. I would like to thank the building safety regulator, the Health and Safety Executive in the UK, who provided funding for this project. And thank you all for listening.